Swayam Prabha. Digital India. Educated India.
Okay, dear students. So last class I taught you different strategy of the signal amplifications. Again, I will continue because there is different class of the signal amplification there. Right? So I will continue few classes like this way using different example. Then only you can understand the whole story because there is lots of design you can make. Huh? So you should know like one by one all the design. Then I will show you how to make the nomenclature of the all the design. So there is some nomenclature also. Make the nomenclature and then I will finally show you the how you can use this one for biosensing like device applications. Okay, so let's come to the next slide. So today I will mainly concept that I will cover, that is the types of redox cycling. So different types of the redox cycling we can cover. So it can be that I showed that we are using actually chemical reactions and with combinations of electrochemical reactions, right. So there can be chemical reactions, then electrochemical reactions, like similar. So we can put different nomenclatures. That's why today actually I will focus on the types of the redox cycling. Then biosensors, some biosensors where we can use this kind of redox cycling. So our main topic of this all the classes is the ultrasensitive biosensor development using redox cycling, and this is mainly electrochemical. Also chemical we are using. Their story I will tell you now. See, last class I stopped here that we can tag the antibody with different material, right. So let's summarize first. So like 3 biosensors I am going to show you. 1, 2, 3. So so see, every cases we can immobilize the antibody. For the receptor we are using just a primary antibody. Antibody 1, antibody 1, antibody 1. So if you add the target here, so it will immobilize. Now the secondary antibody we can tag. Secondary antibody we can tag, but we can label, right. So this label can be enzyme, this label can be some nanoparticles, or this label can be any chemical. Okay. So there is some utility I just mentioned last class. So enzyme, they are very much specific, is very good. There is not much like side reactions because very specific. But nanoparticle case, you have to be very much careful. So you have to design or you have to develop a nanoparticle that should be very specifically, it should react with the substrate. So that's why you have to choose a very specific nanoparticles. And chemical skills also, you can use some chemical that can react with some substrate and it will generate some signal. That part now I will show you, the chemical part. So enzyme part I showed you already, like ALP you can use. Nanoparticle case like gold nanoparticle we can use that with some nitrophenol, last class I showed you. Now we are going to show you the chemical we can use as a tag. So this chemical is the methylene blue. You can see the structures of the methylene blue. Methylene blue has the two species, one is the oxidized form and the reduced form. See, this is the reduced form, it is the colorless, and oxidized form, it is the blue form. So that's why in the next couple of slides I will show you like methylene blue ox, it is the blue color, and methylene blue red, it is the colorless. So this chemical can directly take, because it is a oxidized form, reduced form, so it can take part in the redox cycling process. See, one positive part here, like last classes few slides I showed you, like enzyme or nanoparticles, they are not directly taking part in the redox cycling, but in this case as it is a chemical and it is formed, see, one is the reduced form and the oxidized form, they can directly take part in the redox cycling. So, we do not need any some extra chemical, we can reduce the number of the chemical, right. So, sometime you may ask, sir, if we use the redox cycling, this kind of amplification process, we need many chemicals. Yes, I completely agree, but slowly we are trying how we can reduce the number of chemicals, so that, but still we will get the similar amplifications. Slowly I will teach you this one. At first I showed you that we want chemical. Now I want to show you that how we can reduce the number of chemicals also, but we will still get the similar amplifications. See, so let us show you first actual sensor. So, at the last class I showed you that this is the ALP was used, or gold nanoparticle was used, that is separated, right, it was separate, and it was reacting with some substrate, and it was formed some active material that participated in the redox cycling. But see, in this case, what is the new thing? See, in this case, the tag that I used with the secondary antibody, right, AB2, antibody 2, this is antibody 1, we said that directly participated in the redox cycling, right. So, last time we used some substrate, right, we do not need this substrate in this case. So, necessarily we are reducing one chemical here. See, so methylene blue oxidized form we used. So, this oxidized form can react with the T-shape reducing agent, it can reduce the methylene blue red, the reduced form. And we used here ruthenium hexamine 3 on the sensor surface, and this ruthenium hexamine 3 can react with methylene blue red, meaning reduced form of the methylene blue, and form the methylene blue oxidized form again. So, we are generating ruthenium hexamine 2 plus on the surface, because it is a highly active material, right. So, electrochemical, when again we will apply some potential, it can easily oxidize on the surface and we will get the very high current. So, our problem solved, but we do not want any extra substrate. So, we do not want any extra substrate, and this is at the same time enzyme free, right. Here there is no enzyme. So, this is you can see the left hand side, the complete reactions here. You can design like this way. So, methylene blue ox, that is the methylene oxidized form, you are using with the secondary antibody that can react with the T-shape, form the methylene blue red, and this remains reduced form, and this reduced form of the methylene blue reacting with ruthenium hexamine 3 plus. So, this is reduced form, so it should react with the oxidized form. So, you can ask, sir, why we are not using ruthenium hexamine 2 plus? Because your starting agent should be higher oxidation state, so that it can react with the methylene blue reduced form, right. So, if it is already ruthenium hexamine 2 plus, it is reduced form, this is also reduced form. So, both reduced form cannot react, because this is the chemical reactions. So, this kind of electrochemical or chemical reactions case, when you are generating the high signal in the redox cycling, so certain part is the chemical reaction, certain part is the electrochemical reactions. So, that we can put some nomenclature for that. So, that I will come now. First I will show you the example, then I will come the nomenclature. So, here one chemical reaction, right, here one chemical reactions, and this part electrochemical reaction, right. This is chemical, here also chemical, and this part electrochemical, right, clear. So, like this way you have to choose the all the reagent also, which reagent you should do and which oxidation state reagent you should try, that you can decide by yourself. So, in this case what is the starting reagent then? Ruthenium hexamine 3 plus starting reagent, right, and T-shape, these two is the starting reagent. Why these two starting reagent? See, last cases there is extra starting reagent was there, but in this case we are using less number of the starting reagent. So, we are reducing the number of the chemical, right. So, see the actual biosensor. So, see this image. So, in this biosensor, see what is the signal and what is the background, this should be clarified. So, signal means in the presence of target. So, this is the PFHRP2, a malaria antigen. So, if it is present, then only methylene blue that conjugated with the antibody that will come, right, otherwise it will not be here. So, let us remove it for the background case, but signal case let us keep it. So, if methylene blue ox there, then it will react with the T-shape then this one will react with an hexane 3 plus, it will form the 2 plus. So, this T safe plus methane blue ox plus ruthenium 3. So, I am writing ruthenium 3 because this one is the ruthenium 3, right, ruthenium hexamine. I am writing the ruthenium 3. This is the signal. And background case, so let us leave this one, because it is background. So, this case T safe and 3, this will be there. The 2 will be generated, right. So, T safe plus ruthenium 3, so this will be the background. So, naturally you have to think about these reagents should not react each other, but these reagents should react fast. They should react fast, but they should not react very fast. Then signal will be very, very high than background, and when necessarily your signal to background ratio will be very high. So, again I am saying this one, this is a non-enzymatic biosensor we developed using some redox cycling. So, this redox cycling, the ECC redox cycling I mentioned here, this is the nomenclature that I will come now. So, how we can give a name of these reactions, right. Let us come this slide. So, redox cycling plus electrochemical, these two. See, so here I showed you one, this is just a transducer, this one just a electrode surface. So, here you use the enzyme, something like glucose oxidase as I mentioned, no. So, R means the reducing agent, suppose. So, in this case like last time I used the glucose, right, glucose is the R here, and it forms the gluconic acid. So, O is the gluconic acid, for example. Then here I use the which one, this Q the oxidized form, suppose it is the ruthenium 3, P is the reduced form, suppose the ruthenium 2. You can remember last slides I showed you, like with the enzyme. So, because here enzyme directly taking part in this redox cycling, so I can mention this one here, like why it is redox cycling reactions. Why it is redox cycling reactions? Because P actually generating here from the Q with the help of enzymatic reaction. So, enzyme directly taking part, and so we are oxidizing here, right. Here we are applying some electrochemical potential or some electrochemical behavior that we can see here on the electrode surface. So, this is the electrochemical reaction, right. So, P can be oxidized, it will form the Q, that is the electrochemical part. So, this is electrochemical part, and this part enzyme. So, it is enzymatic reaction, not chemical only, it is chemical reaction definitely, but enzymatic reaction, enzymatic reaction. Okay. So, that is why we can give a nomenclature. So, electrochemical, if it is a electrochemical reactions, we will put E, this abbreviation. Enzymatic case, we will put N, this abbreviation. Okay. So, as it is enzymatic, so this case enzymatic. Okay, let us clear these things, and again I will show you. So, I will put the nomenclature. So, when it is electrochemical reactions we put E, when enzymatic reaction we put N. So, naturally we can give a nomenclature, this one En means from bottom, means from electrode surface to bulk reactions. So, electrochemical and enzymatic. So, it is called En redox cycling. Okay. So, now you can see, sir, if we can increase the more enzymatic reactions. So, here actually see, here I can use some label, that label means some like I mentioned, no, like ALP you can use. So, here you can use the APP, some substrate, it can form the AP, that is also possible. So, something like this, like any kind of reaction you can use, that is why I showed you first some example. But anyway, in the redox cycling, enzymatic reactions and electrochemical reaction, that is all. Now, see, here I will show you the another two example where we can use more number of enzymes, and they will directly take part in the redox cycling reaction. See, enzyme 1 and enzyme 2, two enzymes, so two redox cycling. Here one redox cycling, and then this one can be a redox cycling if you apply electrochemical reactions, means some potential we can apply, but that is we still not applied yet. So, we did not apply any electrochemical, we still not apply here any potential. So, here two enzymes they took part, okay, in the redox cycling. So, here one N, here another N, right. Then see N. Now, if we apply here electrochemistry part, I mean electrochemical part, see here. So, we applied here, huh? See what you can say then here. Then you can say that this is E, this is N, this is N, right. So, we can say this is ENN redox cycling. Clear. So, why this is ENN redox cycling? Because here we applied 2 enzymatic reaction, 1 electrochemical reaction. Now, as I told you that slowly we want to develop some biosensor where we do not want enzyme, right. Let us slowly remove one by one the enzyme. You can see here in this scheme, right hand side in this scheme, you see here one reactions, but here no enzyme. See, it is just a chemical reaction. Last cases we use enzyme, right. This is we use enzyme, but here no enzyme, just a chemical reactions. Okay. So, here we use just a chemical reactions. So, this is chemical, and here we just use, see here electrochemical, right. So, P form the Q after applying some potential. So, this is electrochemical, right. So, here electrochemical, this is chemical, and this P actually form using some reactions, side reaction where we use some another substrate that can react with some tag. That tag can come from the antibody. So, if you go back, I mean I showed you last few, if you go back like to your last class and even today's lecture, some other slides. So, we conjugated your antibody with some tag, right. It can be some label like ALP, or even you do not want ALP, you can use the gold nanoparticle, and with some substrate it will form some P means some product that can be participate in the redox cycling. It is that way, and this can directly participate here. So, here one cycle, but one chemical part, one electrochemical part, right. So, let us put the nomenclature then. Now, we can put some nomenclature here. Okay. What nomenclature we can put here? So, here we can put the nomenclature, it is ECC redox cycling, EC redox cycling, we can put EC redox cycling. Why EC? Because here electrochemical and here chemical, that is why it is EC redox cycling. And here we use which one is the starting material? See, reducing agent R is the starting material, and your P form basically with using some S, and that S react with this label and form the P, then it is it participate in the redox cycling. That is why S is the starting material. Otherwise, P can be your starting material, but we actually P form indirectly using some label and where substrate actually react. Why indirectly we form? Because P is the very active material. So, but S is the very low active material. So, it will create low background. That is why we did not use P as the starting material, we use S as the starting material. So, S and R is the starting material in this case, and it is the EC redox cycling, because it is, see here chemical, here electrochemical. So, electrochemical, chemical, EC redox cycling. Now, come to the another, how means slowly we want to improve the signal amplification. So, more number of cycling slowly we will incorporate here. See here again you can see in this second example, here one chemical again, chemical reaction, here again one chemical reaction, right, here one more chemical reactions. So, there is 2 chemical reactions. So, how you can incorporate these 2 chemical reactions? Again see, so we use S is the starting material that form the P. This P last cases is directly oxidized, but here we will not directly oxidize on the surface, we will use another material O1, suppose like the ruthenium 3 plus, like ruthenium 3 plus. So, that one will react with P and form the R1 like ruthenium 2 plus. So, like this way, so one more cycle we can bring, some extra cycle we can bring, and more amplification we will get. So, one chemical reaction, one chemical reaction. So, this, so here CC, one chemical, we can say CC redox cycling, right. So, it is CC redox cycling. Now, so if we apply now here electrochemical like some potential. So, here it will be electrochemical reaction. So, here electrochemical, here chemical, here chemical. Then tell me what is the name of these reactions? What will be the name of this reaction? It will be ECC redox cycling, right? ECC. So, it will be ECC redox cycling reaction. So, like this way we can give the nomenclature. Okay. So, I put some reference here, please go through these publications also, you will get more details, but I already described everything very detailed way. And now I will give you again some example based on this nomenclature. Now, please try to find out the nomenclatures of the redox cycling. Maybe next class again I will give you some example, you can find out the name. Let us show you some different example. See, here two example I put here. See, you have to try to mention the nomenclature. So, in this biosensor where we use CA, this is a target. So, that is I mentioned many times, and tyrosine, this is a enzyme. Okay. So, this enzyme will react with phenol and form the catechol, and this catechol can be oxidized easily on the sensor surface, and it will form the oxidized form of the catechol. It can release the electron, and this catechol can be reduced by using NADH. So, is it enzymatic redox cycling? We use the enzyme. See, this is the enzyme. Tyrosine, it is a enzyme. And so I mentioned like EN redox cycling and EC redox cycling, these two redox cycling, right. So, because see this one chemical reaction, right, and here electrochemical. So, here electrochemical E, this is chemical C, and this is the enzyme. This enzymatic reaction, tyrosine reacting with phenol form the catechol, this is the enzymatic reaction, but here catechol participating in this redox cycling, right. Catechol participating in redox cycling, not tyrosine participating in redox cycling. So, last time you can remember the glucose oxidase directly participating in the redox cycling, that is why it is enzymatic redox cycling. So, in this case it is not enzymatic redox cycling, right. So, it would be EC redox cycling, chemical, electrochemical. So, here this is the example, see here glucose oxidase directly participating, right, ruthenium hexamine 3 plus form the ruthenium 2 plus, that glucose oxidase actually helping with the reactions with the glucose. But in this case tyrosine is not actually reacting, in this case catechol actually this product actually reacting on the surface. That is why it is EC redox cycling and it is EN redox cycling. Okay. So, this is pretty clear now here. Here one more example, say here we use the secondary antibody with conjugated some nanomaterial. See, this nanomaterial is the not only gold nanoparticle, it has a core of the iron oxide. It means last time we used only gold nanoparticles. Now, here we use some core that is iron oxide Fe3O4 that is decorated with gold nanoparticles. So, it has some different activity. So, that is why you can try different nanomaterial, and you have to choose some substrate that can specifically react with this and form some active material. Okay. So, in this case naturally you can say that it is enzymatic, not enzyme means enzyme based redox cycling, or not is the enzyme based biosensor, it is a enzyme free biosensor, right. This is the nanomaterial we use, and we use here sodium borohydride as a reducing agent, and this sodium borohydride only can reduce nitrophenol to aminophenol if this Fe3O4 gold nanoparticle, this composite present. So, this one specifically actually nitrophenol can be oxidized, nitrophenol can be form aminophenol, I mean it can reduce to aminophenol if this Fe3O4 and gold nanoparticles present. Now, this aminophenol can react with Fc plus, that is ferrocene. This will react with the ferrocene plus and it will form FC ferrocene 0, and then now it will oxidize on the sensor surface and we will get the current. So, now you see this is the electrochemical again, electrochemical, and this one again chemical, because this aminophenol reacting with the Fc plus we form the quinoline, this is chemical, and sodium borohydride react with the quinoline. So, this part again chemical. So, chemical C and electrochemical E. So, just put the nomenclature from surface to bulk reactions like ECC, clear. Like this, so you can put the nomenclature of this redox cycling. Okay. So, see this reaction just I showed you the last like previous slides also, like what is the nomenclature of this redox cycling, right? What is the nomenclature of this redox cycling? Now you can easily interpret. Last time I told you ECC redox cycling. Why ECC? See, here no enzyme, right? Here methylene blue itself is participating. So, we conjugated methylene blue with the secondary antibody, it is directly participating in the chemical reactions. So, methylene blue ox reacting with T shape, it form the oxidized species, and this one methylene blue become colorless methylene blue red. So, this is chemical. Again methylene blue red means reduced form is reacting with ruthenium hexamine 3 plus, means it is oxidized form of the ruthenium. So, this is again chemical. And here we are applying some potential and we are getting the electron. So, it is electrochemical. So, this is C, and this is E. So, it is ECC redox cycling, clear. So, why we put the ECC redox cycling for this biosensor. So, in the conclusions of this, so up to now today I taught you the nomenclatures, right, how you can put different name for the biosensor where we are using the signal amplifications, like, so I taught you today like EN redox cycling where we can use enzyme, and these enzymes should directly participate in the redox cycling. Then EC redox cycling, EC means electrochemical and chemical. So, here you can use enzyme, but that enzyme should not participate directly. So, in this case this redox cycling is the enzyme free, but this redox cycling is not enzyme free. Even you can but EC redox cycling can be enzymatic biosensor, maybe non-enzymatic biosensor. Like suppose if we use the gold nanoparticle, in this case it is enzyme free, but if you use ALP for generating the AP active species, then it is not be enzyme free. And I taught you today ECC redox cycling, electrochemical, chemical redox cycling. So, if you see many examples, again I will show you the next classes few more examples and more practical applications where we can use this EN, ECC, EC and ECC redox cycling. I will give you some practical example in the next class where you can see that easily we can amplify the signal, and there is lots of applications. So, and from all the application case, we can summarize that ECC actually always much better than the EC redox cycling. Why? Because here is the more number of cycle actually we are using, and they can enhance the electron transfer rate on the sensor surface. So, this can be useful for the, that is why very much ultrasensitive biosensor by using ECC redox cycling. Okay. So, that is all for today. Thank you very much for the this ultrasensitive biosensor using different redox cycling. Next class I will teach you more applications using this redox cycling reactions where we can develop more biosensor. Thank you.